Okay, this is chapter 4. What we've all been waiting for. All of our questions about stars hopefully will be answered. So we'll start with classifying stars. This is section 4.2. We skipped the first section in chapter 4, which I will not put up on PowerSchool, but for those of you that didn't take your books home, I will post the teacher's edition of this particular section, which is on classifying stars, because there will be an assignment that goes, a worksheet that goes along with this that you can either pick up at school or that you can print off or just pull up on PowerSchool Learning and then just answer the questions. And I'll leave some notes as to which questions I want you to answer, because I'm going to take a few of them off for these, just because I'm not in class to answer some of the harder questions or to help you with harder questions. So you'll see I'll cross a few of them off on each of the worksheets. Not much, but just a few. So we'll start with classifying stars, like I said. So when we classify stars, we use a couple different characteristics to classify them, including the color, the temperature, the size, the composition, and the brightness. When we look up in the sky, they kind of all look the same. I know in the book it mentions, you can kind of see that this one looks blue-white and this one looks more reddish, but unless you have a telescope, you might not necessarily see the differences in colors, but astronomers can. So when they look into their telescopes, they can kind of see those. In fact, a spectrograph is mentioned in this section on page 128, or the third section of it. And the spectrograph really can help to tell what the composition is, and the composition also tells a little bit about how hot it's going to be. It was always confusing to me when I first started learning about stars, because when I think of hot, I think of red, I think of orange, I think of yellow. But actually, your hottest stars are blue. So blue hot is actually going to be the hottest stars that are up there. Some of your bigger stars are cooler than some of your less big stars. So for instance, our sun, which is medium sized, as you can see in the picture here, is yellow. And a big giant star is red. Well, red is actually the coolest type of star, whereas this larger star here that's blue, that's a hotter star. So depending on the color, so again, you'd have to look in some sort of a telescope to kind of see these colors a little bit closer. I mean, to me, they all look like they're white stars when I look up in the sky at night. They look white to me. But they obviously do have different temperatures based on, basically on their composition, because these gases are mostly made up of helium and hydrogen, and as they burn through those gases, depending on how much they have left, some of them will have more gas left than others, and when it burns, it's going to have more fuel. If it's a star that's a little bit newer, it's going to have more fuel, so it'll probably burn a little bit hotter than some of those other stars, depending on that. The hottest stars can get over 20,000 degrees Celsius. Put that in somewhat of a thought for you, because it's a really, really large number. Boiling point here on Earth is 100 degrees Celsius. We're talking about, 2,000 times greater is the surface temperature of some of our hottest stars. Some of your cooler stars is about 3,200 degrees Celsius, and about in the middle, our sun, which is about 5,500 degrees Celsius. So it's right there in the middle. The size, from the smallest to largest, they go from neutron, which is basically a star that's just in its beginning stages. Then there's the white dwarfs, which is the smallest, medium-sized, and then there's the giants and the supergiants. We're a medium-sized star. The smaller stars are called white dwarfs, and neutron stars are basically just as they're starting to get going. And then supergiants, you can't really see. If you look at the picture in the book, you'll see a little bit better. It's pretty big. It's so big it can't really show up in this picture if we're talking about scale-wise. Okay, so like I mentioned, the spectroscope tells us a little bit about the composition. So depending on what type of gases make it up, some bigger stars have more gases in them than, say, our size star, which is a medium star. We just basically are hydrogen and helium. But the bigger we get, we can talk about things like sodium and calcium being inside those as well. Of course, they're not probably, sodium and calcium are usually solids, but they can be more gaseous at this point as well. And so if we look through a spectroscope, if we're looking at a star, we can kind of start to talk about what different gases are involved depending on what that spectroscope sees. Brightness of stars would be that second part of this section, and brightness of stars basically depends on the size and its temperature. And this picture that I kind of took out of the book here talks about absolute brightness, which is basically how much brightness it actually gives off. Apparent brightness is basically if we look out in the star, we can talk, or I'm sorry, out in the sky, we can talk about one looking brighter than the other. So apparently it looks this bright, but if we're talking about specifically how bright it is, we talk about absolute brightness. So I think we talked about this before in other scientific terms. I know we talked about with fossils, what do they appear, their absolute age versus like the age they are compared to something else. So that's here, the same thing. So how bright they actually are absolute. How bright they appear to be compared to other things, we can talk about their apparent brightness. And again, the brightness of stars is going to depend on both the size and the color of it. I'm sorry, size and temperature of it. It's going to tell us a little bit how bright it's going to be. And again, a lot of this depends, for us, at least here on Earth, how far away it is from us. Because it could be a super bright star, but since it's super far away from us, it doesn't necessarily appear as bright to us, which is that apparent brightness stuff. To really understand the brightness, we'd have to kind of start to talk about what is it made up of, how big is it, things like that. So we'd have to study a little bit more about these stars. Okay, we've always talked about how massive and humongous space is, and so to talk about distances, we don't necessarily talk about distances the way we think of like miles or yards or anything like that. Instead, we can talk about light years. So light years is the distance light travels in a year. And that helps us to determine how far it is from one place to another out in space. So that is just one way that they use, that is the main way that they use to measure distances to stars. Because again, it's so vast out there, they had to come up with a really large number for us. And I think this is the place where it mentions that the closest star to us is Proxima Centauri. It would take about 4.2 years for us to get there if we went at the speed of light. So that's how far the closest star is to our sun, 4.2 years away, going at the speed of light. So the speed of light is actually 300,000 kilometers per second. So it travels about 9.5 million kilometers in a year. I know we don't necessarily talk about kilometers, but a meter is about a yard. So take out, if you start thinking about, oops, sorry about that. So if we take out, if we start talking about like how big that is, we're talking about how far it travels. We're talking about a really, really large number. So it's kind of just almost hard to imagine how big these spaces are for us out in space. I think this is always an interesting thing to talk about. This is a parallax. So a parallax is something that's like an apparent change in position. And that can happen as our Earth is rotating and revolving. The stars stay in one place for the most part, and so as we're traveling, things look different. They appear in different parts of the sky at different parts of the year, which is kind of what this is showing us here. So where the Earth is in January versus the Earth in July, and it kind of talks about how things look. Like A looks closer to B here in July than it does over here in January. A and B are pretty far apart. C and D are about the same no matter what, but you can see they kind of seem to like trade places in the sky or move around. It's us that's traveling and moving on, not so much them. This other one I always thought was interesting too, this little comic that they have in the book. In your view versus your friend's view, it could be completely different. So depending on where you're looking at, it depends on what you see. So that's what a parallax is. It's an apparent change in position if you look at it from different places. So that's why it's talking about a parallax when we're talking about the Earth in July versus the Earth in January. Because it's a completely different place where the Earth is located. So we're in a different space, so things look a little different. This helps us to measure distances to nearby stars depending on how that change takes place. And we can start to talk about like how far that is based on, where it appeared in January versus where it appeared in July. So some of this stuff, it takes a really long time to really get these measurements. Okay, so this is the last little part of this section. It's called the Hertzsprung-Russell diagram. A couple different scientists worked together on this one. One of them was in Denmark, one was in the United States, and they both basically came up with the same diagram, not necessarily working together, worked independently of each other, but basically came up with the same diagram. And this shows how temperature and brightness are related to each other, and then again it's used to classify stars. There's this part called the main sequence, as you can see here, and this is where most of the stars fall in. It's just this little area right here. And so these would be like your medium-sized stars for the most part. Then we've got our white dwarfs up here, our giants, and of course our supergiants up here. And you can see that your hottest stars are going to be some of your ones, either the main sequence or the white dwarfs, whereas they're a little bit cooler in this area. Some of these are. We don't have any of them that fall all the way over here in our supergiants. In fact, our giants, none of them fall over in the hottest area, the hottest surface temperature. But anyway, so how are these things related? So the temperature is going up this way. So from red all the way to blue, remember blue is the hottest. So temperature goes up this way, whereas brightness goes up. So it goes from like left to right here in the bottom, but it goes from down to up on the top. So this just talks about how bright it appears versus its surface temperature. Remember that these are different parts of the sky, so it's not exactly showing you exactly where in the sky it is, but just where it falls on this diagram. So most of your stars are going to fall in there. So 90% of the stars, including our sun, which is right here, falls in this particular set of main sequence stars. Again, you are welcome to read about this. Probably some of the answers that you will get probably won't come from this lecture. They might come from in your book, as usual. But I just wanted to kind of give you some insights to what you're reading and things like that. Again, this is posted, the reading is posted on PowerSchool Learning. It's a PDF. You'll also have a worksheet over this where you can either, like I said, print it off and hand it in. You can pick it up at school, or you can just take the answers and write them on a separate sheet of paper and turn that in as well. And like I said, when I go to actually post some of this stuff, I will put which numbers you do not need to do in your worksheet. All right. Have a good day.